So it's recording now. Let me see. Okay. So welcome everyone to come to the first CNTC seminar in the 4th semester. It is my great pleasure to introduce Professor Andrea Young from UC Santa Barbara. Andrea is an expert experimentalist specialized in two-dimensional materials and quantum Hall physics. He did his PhD in Columbia University and a postdoc in MIT. And since 2015, he has been a faculty in UC Santa Barbara. Andrea won many including William McCamilla is going to tell us about recent experimental progress.
Thanks, Youngji, and thanks for the invitation to Maryland. I'm very sorry not to be able to visit in person, but hopefully in the near future, I'll be back in my hometown. So, so today I want to tell you about some of our recent work on orbital magnetism and related effects in twisted bilayer graphene. So I'll try to cover a lot of ground without too much going into too much detail, but I put here some of the most relevant references, and let me acknowledge up front that we did the experimental work here, which were Marek and Gregory Polsh and Yu Saito, who always the key experiments going. So I think everybody, I'm not going to give an extensive introduction to moire materials or twisted bilayer graphene in particular, under the presumption that a condensed matter theory seminar, by now everybody's sort of familiar with the basics. The basic picture that I want to just to remind you of what the points of interest are is that these are systems in which one can make relatively flat bands at zero magnetic field. And one of the key, so we've of course studied flat bands in Landau levels for many years, but having flat bands at zero magnetic fields opens up sort of two obvious, interesting new directions, which are the study of phenomena that are normally kind of antithetical to observation at high magnetic fields. In particular, superconductivity, which is usually suppressed by magnetic fields, was observed in twisted bilayer graphene in 2018, and ferromagnetism was observed in a very similar system in just shortly thereafter. Both of these are things that, in their purest form, are not obviously evident in Landau level systems, although they are sort of variants of both that exist there. So I'm going to mostly talk about orbital magnetism and come back maybe a little bit to superconductivity at the very end. And so what is different about these two situations, right? In fact, to date, superconductivity and magnetism have not been observed in the same sample. So let me sort of give you an example of where, just to walk you through what experimental data in the system tends to look like. So here's a measurement of a twisted bilayer graphene sample. What you see, this is measured at high temperature, let's say a Kelvin or so. And you can see that we're plotting things here as a function of charge carrier density, and above is indicated the number of electrons or holes per superlattice unit cell. And you can see there are resistivity peaks at charge neutrality, and then at nu equals 2 and 3, and also at nu equals -2. That's sort of a typical phase diagram of twisted bilayer graphene. And the basic physics of the system is that as you cool it down, you typically get a region of superconductivity near nu equals -2, a weaker region of superconductivity near nu equals +2. But this is basically what the system looks like in the sort of most commonly realized form. The first part of the talk, I'm going to tell you about what happens under slightly different circumstances. So these samples are made by twisting two layers of graphene together. You assemble them one step at a time with a twist angle that you can determine approximately experimentally. And then they're sandwiched between hexagonal boron nitride encapsulating layers. These are both this is sort of standard technology for making clean graphene heterostructures. But as we know from studies of monolayer graphene, actually the hexagonal boron nitride itself can change the graphene electronic structure. And in particular, this is strongly dependent on whether this hexagonal boron nitride crystal is aligned or strongly misaligned from a graphene layer. It has the effect of breaking the sublattice symmetry in the graphene layers when it's closely rotationally aligned to them. And so it turns out that in monolayer graphene, what happens is that this opens up a gap at charge neutrality, and that's basically the effect of that hexagonal boron nitride substrate. It turns graphene from a gapless Dirac semimetal into basically a semiconductor with a gap that can be rather large, on the order of 30 MeV or even more under certain circumstances. So interestingly, in twisted bilayer graphene, where the overall bandwidth is of that same order of 20 or 30 MeV, you get even more dramatic effects. So in particular, what I'm showing here is the same type of plot that I showed you before, plotted as a function of charge carrier density. You're looking at the longitudinal and Hall resistance of a twisted bilayer graphene, in which the twisted bilayer is rotationally aligned to one of the hexagonal boron nitride substrates. And this looks very different. So let's focus first on this sort of cyan curve. You see that there's a weak resistivity peak near 2 electrons per unit cell, not much action at -2 electrons per unit cell, so already quite different. And then, and this is where the sort of most interesting finding is, there's actually a resistivity minimum at 3 electrons per unit cell. And if you look at the Hall effect here, measured at very low magnetic fields of a couple hundred millitesla, you find that it seems to be quantized to just around the quantum of resistance. And it turns out that if you look closely, meaning if you do a if you look for magnetic hysteresis at this filling, you can find that there's in fact a quantized anomalous Hall effect. So what I'm plotting here are field rising and field falling traces of the longitudinal resistance, which is 0 at 0 magnetic field, and the Hall resistance, which is quantized to either plus or minus h over e squared on the 2 branches of this hysteresis loop. So this is what's known as a quantized anomalous Hall effect, right? It basically suggests that the system is polarizing into some number of bands with a net finite Chern number. To do that, it has to break time reversal symmetry. So this is basically a magnet that in which an integer number of bands are filled, and so that sort of makes sense. So this is sort of a schematic picture of what this looks like. So the
Andrea,
yeah,
this is Shankar.
sure.
Could I ask
Hi,
you,
Shankar. Yeah.
Is there any hope in 2-dimensional systems? It's very difficult, I know that, but you guys are very smart. Is there any hope of a direct measurement of magnetism? These are all very nice measurements, but I'd call them indirect. Direct is a divergence susceptibility or something like that. So one has to do kind of measurement that,
Yes.
Einstein did exactly once.
Let me come back to that. I think that we have a pretty direct measurement of magnetism that I will show you.
Okay, all right.
In
so
a few slides.
We'll come back to that at the
To
end of
ask
the
about divergences of susceptibilities, I think the short answer is yes, but we haven't done that particular thing. But we have imaged magnetic order, which is it's coming soon. So maybe
right,
hold your question.
We'll talk about it then. All right. Thank you.
Yeah. Let's talk about it. So the basic, before I get into sort of the a deep dive into experimental data, the basic picture here, I think, is theoretically is reasonably simple, which is that you have a system with rather small bandwidth. So Coulomb interactions are comparable to this bandwidth. Ferromagnetism is a natural is a natural ground state for electron-electron interactions. And the key feature of these aligned samples is that it opens up a relatively large gap between the conduction and valence band. And since you're gapping out a Dirac point, the way that Dirac point gaps out is to generate finite Chern numbers for these different subbands. Of course, the Chern numbers cancel in the opposite values. Here it's shown for spin-degenerate bands, so they have a Chern number of -2 or 2 in one valley or the other. And then the picture is that when you turn on interactions, there may be a ground state at, let's say, 3 electrons per unit cell, in which you fully fill one of these valley projected Chern bands. And apparently from experiment, one would say this must be what's going on, because we see a quantized anomalous Hall effect, which you would not see, for example, if you had some ground state that was a superposition of states in the two different valleys. Interesting features of these magnets, besides that they have a finite Chern number, after all, quantum anomalous Hall effects have been observed, although in very different systems, as I'll discuss, is that most of the time one gets ferromagnetism from strong interactions, fine, and spin-orbit coupling, which is what gives you anisotropy. And very interestingly, in these systems, there's likely very little role of the spin at all. There's almost no spin-orbit coupling in carbon. So you have something that looks like an icing ferromagnet in some regards, but is not probably based on the electron's spin at all. It should be essentially a purely orbital magnet, where this is really valley polarization. Spin is kind of playing a secondary role, if anything. And in fact, if you just naively ask whether the spins are ordered or not, based on naive estimates of what the spin-orbit coupling is in the system, it's not entirely clear that they would order at the temperatures at which these experiments are done. So, so it's a rather different type of magnet than sort of your normal, exchange plus spin-orbit coupling, iron or any other type of magnet. So, sort of experimentally, there are some very nice features to this. So one is that it's actually quite a robust effect. So you can see that quantization is quite good at 1.5 Kelvin. It stays good at 4 Kelvin. It starts to degrade around 6 Kelvin, and then it rapidly disappears. And that's true of both the Hall and longitudinal resistance. Also, at the lower temperatures, you can see these discrete steps that are visible throughout the hysteresis curve, reminiscent of Barkhausen jumps coming from some sort of relatively small number of discrete domains. You can look carefully, and these samples are very hard to make. We've in fact not been able to reproduce another sample that looks exactly like this, although of course we can measure this sample all day and it always looks the same. The quantization is very good. It's mostly limited by contact resistances, so a few parts per thousand. And that allows us to actually measure some activation energy scales for the electronic energy gap, which we find from RXX and RXY to be of order, well, 30 Kelvin plus or minus, a few Kelvin. So that's, again, quite large compared to other quantum anomalous Hall systems. And it's particularly large given that the magnetism seems to disappear right around 8 Kelvin. So here's plotted on a so-called arrow plot or arrow plot. I'm actually not sure how to pronounce that name, where you're looking at R squared, RXY squared as a function of magnetic field divided by RXY, and basically where these lines sort of change their form, that's where you would say the Curie temperature is. So here it's somewhere around 7 or 8 Kelvin, considerably smaller than the energy scales of the electronic, essentially the activation scales of the electronic part of the system. And this is really a different scenario than, let's say, conventional quantum anomalous Hall systems, meaning where the experimental system where this effect was first realized in transition metal doped topological insulator thin films, where the Curie temperature is quite large, 20 Kelvin, but the activation gaps at most are about a factor of 5 to 10 smaller than that. Here we have a Curie temperature of, okay, this should be probably 7 or 8 Kelvin, and activation several times larger. So this turns out to be more or less in line with theoretical calculations for a clean system. And I think really the difference here is disorder. This is an intrinsic effect, we think. It doesn't come from dopants, whereas here you're trying to take a non-magnetic system, making it magnetic by very strong, on the order of 10% alloying, and it's not even clear that the alloy is really an alloy. It may be sort of interstitials. It's a rather disordered system. So just from that practical point of view, this turned out to be sort of nice. You don't need very low temperatures. But there are a variety of other qualitative features that we observed in this and related systems, which I'll show you, that that I think maybe are more exciting. So I just sort of want to flash a few of these findings. One is that it turns out that these systems, I think this is not something that actually we fully understand, but roughly speaking, I would say the message that I'll try to impart is that because these are orbital magnets, the nature of pinning and the nature of how you can actually manipulate them are quite different. So here, what I'm showing you is another hysteresis loop, but this is actually measured not as a function of magnetic field, but rather as a function of current that you pass through the sample at zero magnetic field. And you can see that very, very small currents are sufficient to reverse the magnetic order nearly between the quantized values. This is taken at rather high temperatures, rather close to the Curie temperature, to suppress some of the pinning of secondary domains. So we're just left with one domain. And you can see that just a couple of nanoamps is enough to flip you from one side to the other. And this means actually that you can make a little bit if you want. So you can put little current pulses. And what I'm plotting here is a function of time. Every time we put a little current pulse of 20 nanoamps, we can flip our bit up and down and up and down. And then you can let this sit there and it's stable for as long as you're willing, to wait. So it gives you a little current switchable magnetic memory. Too hard to make one of these samples to consider starting a company, but I think there's sort of an interesting fundamental question here about what exactly the mechanism is here. There's been a few papers on arXiv since, and I would say that we don't understand that very well at this point. So I'll just sort of submit it for your consideration to think about. So let me sort of change gears slightly and sort of tell you about experiments that are ongoing to try and understand this a little better, because one of the questions that one could ask is whether this is in fact the same magnetic switching. Do the same domains flip when you pass a current versus when you change a magnetic field? So to do that, we set out to try to image this ferromagnetism directly, so we could try to understand the microscopic structure and the coupling to disorder. This is a challenging problem because the moment densities are quite low. You'd expect something on the order of Bohr magneton per superlattice unit cell, but of course the superlattice unit cell is very big compared to typical lattice unit cells, which means that the moment density, which in 2D is just measured in units of current, is about 50 nanoamps. If you have a magnetic sensor, let's say at a distance of 100 nanometers, then you're going to be looking for nanotesla magnetic fields, and there just aren't very many tools that can do that. One of them is nanosquid on tip microscopy. So this is a technique that was developed by Eli Zeldov over the last decade, in which you fabricate a squid on the tip of a quartz pipette. And then that turns out to be a very sensitive magnetic field sensor, excellent noise performance, but also allows you to bring this tip very close to, let's say, a two-dimensional sample. So we've actually been building up this, this technique in my lab, and what I'm going to show you are data from an indium nanosquid on a tip. It has a diameter of about 200 nanometers, a magnetic field noise of about 15 nanotesla per root hertz, which means that, you know, in less than a second, we can detect these types of magnetic fields. And it operates in kind of a convenient temperature range and magnetic field range precisely for studying this, this type of physics. So before I show you data, I have to just tell you how the measurement works. In order to get that noise performance, you need to be able to measure a signal that is modulated at a relatively high frequency of a few tens of kilohertz. And for static magnetization, as in twisted bilayer graphene, which is basically a metastable phenomenon, you can't really modulate the signal, right? So you have to modulate something else. And the way we do that is to mount this is our squid on tip, and it's mounted to a tuning fork like you would have in a digital watch, a quartz oscillator, and that basically you can use you know, an electric stimulation to make the tuning fork and therefore the tip oscillate back and forth. And you can make these with very high quality factors so that they work very nicely. Also, they provide us topographic feedback so we know exactly how far we are from the sample. And so then as a result, what you do is you measure, basically you excite the tuning fork so that the tip is going to vibrate, and then you measure the response of the squid at the frequency of those vibrations. And that gives you a signal that's proportional to the gradient of whatever the static response is projected in the direction of that tuning fork oscillation. And you can calibrate that by looking at some large signal. And we usually use a thermal signal. These are also thermal thermometers, so you pass a large current. And you can reconstruct the tuning fork voltage from gradients of the DC signal. And then now we can take that and apply it. So what I'm going to show you are actually the direct measurements are measurements of this gradient of the magnetic field. So, so this was a very hard experiment to do. In particular, these are very small signals, and there are lots of backgrounds. So one of the key things that we need to do is to look at difference measurements. So So what I mean is here are actually measurements of our device that's in this region of the device. These are exactly the contacts that show our quantized anomalous Hall effect. And what we do is we measure it at the same magnetic field, but once having prepared the state in the positive Hall state and the other in the negative Hall state. And so these are measurements of the two. And if you look closely, I'll probably go through it too fast for you to correlate every dot. Most of the things that are blue down here are red up here. If it's red down here, it's blue up here. So you have indeed changed the sign of the measured signal by changing the sign of the Hall effect, even though this is measured under the same conditions. So this looks like indeed you've flipped the underlying magnetization. So you can take differences of these two images to get what corresponds to this measurement of the tuning fork magnetic field, meaning the gradient along this direction. By the way, this is the direction that you are taking a derivative of the DC magnetic field. And that basically produces something proportional to the derivative of the DC magnetic field. Now, if you have the derivative of the DC magnetic field everywhere, then you can use basically standard kind of Fourier domain techniques to reconstruct the DC magnetic field, and then assuming out of plane magnetic moments only, the underlying magnetization density, which is what we want. And here it's expressed in 4 magnetons per unit cell. So so this is basically what the sample looks like, right? We think magnetically in the fully polarized quantum anomalous Hall state. And I guess one could say that it is a tribute to the power of topology that this system shows beautifully quantized RXY. Just as a side note, for those of you who are looking with eagle eyes, it doesn't look beautifully quantized here. That's because the contact geometry is not ideal. So there's some mixing of RX and RXY. Contact resistances are also high. In order to get nice quantization, one needs to very carefully use Onsager relations and measure at exceptionally low currents and so on. And when we're doing the scanning measurements, we tend to not take that care. So it's the same sample, same measurement. This is indeed a quantized state if you're careful about how you do your transport measurement. But the bottom line is that this is the magnetic structure. It's not particularly uniform, but before I get to sort of dealing with some of the effects of non-uniformity, let me just point out that this gives us a quantitative measurement of the moment density, and it is something like 4 Bohr magnetons per unit cell, and this is measured at effectively 1 electron. It's at nu equals 3, which I would say is 1 hole per unit cell relative to full filling. So 4 Bohr magnetons per unit cell is more than you could possibly get from spin in any reasonable picture, which and potentially much more. As a result, we are relatively convinced that indeed this is sort of evidence that this is an orbital magnet fundamentally, right? And 4 Bohr magnetons per unit cell is well in the range of what it's a big range that theory has predicted for exactly how big those moments should be, but 4 Bohr magnetons per unit cell seems to be in the middle of that range. So it's not an unreasonable thing from a theoretical point of view either. Just to show sort of some of the things that one can do, because there are these discrete jumps in Hall, we can try to use them and perform sort of minor loops to try and stabilize different states at the same magnetic field, which is where we measure. And so we can measure, for example, a state with a nearly quantized Hall of one sign, nearly quantized Hall of the other sign. That's what I showed you, but also something that has, for example, a Hall effect of about 0. And then we can analyze differences of these pairs. And you can see which domain flips in the middle, right? And it makes a lot of sense. You basically are flipping half the sample, and then you flip the other half of the sample. And that's what these discrete steps in the Hall resistance correspond to. So you can basically now reconstruct what this looks like. One of the conclusions that we get from this, for example, is that in fact it seems as if potentials equilibrate quite strongly along these chiral domain walls, so that these edge states indeed are in equilibrium. That's one of the things that comes out from the fact that you have RXY equals 0 in a domain configuration that looks like this. Okay, another, so, you know,
Hey, Andrea.
Hey, Jay.
Hey, just quickly, so the magnetization doesn't seem to be negative anywhere, does it?
It's not, but what this
right-hand
measurement is, just to be clear, right? This is a measurement of the difference between this and that.
Yes.
So, you know, this is sort of fully polarized up. And so,
okay,
indeed, it doesn't seem to be
Ha, ha,
negative
ha, ha.
anywhere. Yeah, at least,
Right.
you know,
I see.
not
Okay,
beyond
so you can't.
our systematic errors. Yeah.
I see. Oh, but so the difference is always positive by definition. Is that what you're saying? Or?
Essentially, yeah. I mean, it's
Yeah.
possible that we could have gotten. I mean, it's not like our measurement can't generate negative values, but it would be. It would be somewhat unusual to find that essentially we are measuring the difference between these two states. You would have to have something sort of strange going on. This is the difference between full polarization and, you know, opposite full polarization.
Yeah, good.
Nothing about our measurement precludes that, because, you know, we are referencing this to the differences far from the magnetic region. So zero is a true zero here.
Yeah.
But yes, it's not negative anywhere. Here again, these are differences sort of reference to this E curve, or, you know, to the higher of the two curves. So you don't really expect it to go very negative. Okay, let me show you some, you know, so another thing that we can try to do is to just look at the density dependence. So everything I've shown you so far is actually measured more or less inside this gap. Actually, it turned out we weren't measuring precisely in the middle when we were doing all of this exhaustive data taking. But what you can do is now take a line cut across some small piece of the sample and just look at how that evolves as a function of carrier density. And what's plotted here in blue with you know, these sort of cyan dots are just the hysteretic part of RXY. So in other words, you know, difference between magnetic field preparation sweeps. And you can see this is basically the quantized plateau is in this narrow range of densities. And white is essentially an average of how much internal magnetic structure there is, and which we take as a rough proxy for the magnetization density. And what we find is that on one side of the gap, it's relatively large. You know, you see a fair amount of structure locally, even when the Hall is not quantized. But then as soon as you get into the quantized Hall gap, this drops essentially to zero, even when you can still observe some hysteretic transport. So there's an interesting idea for how this might come about that sort of appeared from Alan McDonald's group on arXiv right around the time we were doing these measurements, which is pointing out a very simple fact, which is that topological edge states contribute something to the magnetization. In particular, for a given Chern number and a given energy gap, you will have a net change in the magnetization as you cross that gap that's simply proportional to the 2 divided by the flux quantum. That's some number, right? It's not a very big magnetization density. It almost never matters in systems like, chromium dope, you know, bismuth, antimony, telluride, because the bulk magnetization from the spins is many orders of magnitude larger than that. However, in an orbital magnet, this is just not that different from the bulk magnetization, which you get as you fill the bands. And depending on details, they can be comparable. And indeed, this one can even be larger, and typically it has opposite sign. You know, roughly what we think is happening here is that as you cross this gap, you know, the edge states are all that's contributing to the magnetization. They appear to be nearly canceling the magnetization that you've accumulated as you empty that one finite Chern number band. This is somewhat, I mean, it's a direct measurement of M in a sense, but it's actually not the most spectacular effect that one can see arising from this basic insight. To show you that, though, I have to introduce a slightly different moire system. So let me digress for a few moments and tell you about twisted monolayer bilayer graphene. So this is a system that has a monolayer of graphene twisted at some small angle on top of a Bernal bilayer. Why do this, you might ask? Well, you know, when you discover a new continent, you sort of want to catalog all the animals in case any of them are useful. And there was sort of similar work on double bilayer graphene that found that, well, you sort of have these sort of correlated insulators also. And the motivation here was that what we our intuition was that from the twisted bilayer graphene on hexagonal boron nitride, sort of a key point was broken inversion symmetry coming from the BN substrate. And that's sort of hard, that's hard to reproduce because it's hard to align graphene to hexagonal boron nitride. However, in this system, you sort of naturally have a lot of symmetry breaking because you have a monolayer on top of a bilayer, so you certainly don't have any symmetry between the two active layers. So the hope was maybe this would be an extreme case of that where you could tune it and you could really see what's going on by through displacement field where you push, this is the electric field applied perpendicular to the two layers. You push electrons to the top layer or to the bottom layer. And indeed, these measurements show that you can get correlated physics. So once again, this is as a function of charge carrier density, and this corresponds to nu equals 1, nu equals 2, and nu equals 3 inside the system. So there's clearly, interaction-driven physics going on in these partial filling states. But actually, the sort of spectacular thing here is that these turn out to be quite robust quantum anomalous Hall states again. Okay, so I'm showing data at nu equals 1 and nu equals 3, and you can see that the Hall resistance is nearly quantized. The data is not spectacular in terms of the degree of quantization, but you have Hall angles of 88 or 89 degrees, basically no RXX, very large RXY, and these plateaus disperse in magnetic field in agreement with the Strata formula for a Chern number of 2, which is also what you see in the Hall, and is also incidentally what you expect from band structure models. In this sort of 3-layer system, you end up with Chern band of 2 and Chern band of -1. That's sort of how you basically, there's a wide region of parameter space for band structure modeling that that seems to produce those types of Chern numbers. So it's maybe not so shocking. But what I want to bring your attention to that was really unusual in this system is what's going on at nu equals 3. So if you look at this experimental data, and this is what we said, I just thought there was something wrong with this device. It looks like there's a contact that's bad. There's a lot of switching going on. As you try to measure this, the Hall effect is actually reversing signs basically all the time. No matter what you do, you change the field, it switches sign. You change the carrier density, it switches sign. It basically looks like you've got a contact that's just broken or intermittently broken. I mean, it's sort of experimentalist's worst nightmare that you can't measure the same thing and twice and get the same answer. But that turns out to be actually a feature and not a bug. So after we sort of dug into this and looked really carefully, we realized that in fact, it's what it looks like, that the magnetic field, so here I'm sort of plotting this on a strange 3-dimensional plot where I have magnetic field and carrier density. So if you choose a carrier density and sweep the magnetic field in blue and green, you're basically seeing a typical magnetic hysteresis loop. But, and this is the really strange thing, if you sit at a finite magnetic field or 0 magnetic field and sweep the charge carrier density, you also produce a hysteresis loop. Okay, and that's really unusual because usually, changing a carrier density doesn't change your equilibrium magnetization. But here apparently it does. And again, we think that this actually is quite consistent with this picture. So that the idea here is that you have some contribution to the magnetization from the edges, which is C delta over phi naught. And if M of the bulk, let's say at the band edge, happens to be around half of this value, then in the gap, you can simply switch the sign of the overall magnetization, which means that in a finite magnetic field, you now have switched from, you want all the moments polarized into the K valley and A sublattice to the opposite sublattice or opposite valley. Okay, and if there's disorder and pinning, then you'll have some hysteresis. And when you overcome those barriers, you will switch because you've actually tuned the sign of M in a given valley. You've now reversed them. And now the ground state has switched to being in the other valley, even though you haven't changed the magnetic field. You just switched the sign of M overall. So this you can also play fun games with, right? So this is another plot of the type I showed you before. This is just as a function of time. And what we're doing is we're alternating between sweeping, doing little pulses of gate voltage, right, which reverse our magnetic bit, or doing little pulses of magnetic field where we sweep across these hysteresis loops, right? And you can do this, again, all day long. In this case, I guess, whatever, 6 hours was as much as we had patience for, but you can do, you can basically use either charge carrier density or really chemical potential, because I think in the gap, you're not changing the carrier density very much, or magnetic fields to reverse your magnetic bit. So I'm going to change gears slightly and show you kind of a different type of data for the last part of the talk. So this is the same system. So I'm just going to show you what happens to these systems at finite temperature, because this has also become a point of interest in these systems. So, so yellow is just a line cut across this region. And I want to sort of just to reorient you. What we think is happening is that for electron filling in this system at a given displacement field, you have a sort of small region where you create an isolated narrow band. And that's where interaction effects are really important, okay? And that's where you see all of this physics that's kind of obviously coming from interactions. For hole filling, we don't think that interactions are terribly important. If you take, there are actually features here which you can look at in more detail. They're correlated with Van Hove singularities in the band structure, and they match single particle calculations reasonably well. So we think for the most part, this is kind of a regular metal, and over here you have something kind of exotic going on. So now you can take that cut and you can measure things as a function of temperature, and you can see that these types of commensurate filling phases emerge at 10 or 15, 20 Kelvin and so on. Not much action in the sort of uncorrelated side of charge neutrality. Now, if you plot line cuts as a function of temperature in these different regions, you actually see something pretty striking, which is that, not only does an insulating state emerge, let's say at nu equals 2, but actually you have very big changes in the resistivity of the metallic phases that are, within these halos that seem to be associated with that. So it seems as if when the system orders magnetically, and we know that these are ferromagnets of one kind or another, you get a big change in the resistivity, right? In this case, it changed by basically an order of magnitude, and under other circumstances that can be even bigger. And that's sort of, I think we think that this looks a lot like superconductivity, but is not superconductivity. And in fact, a lot of people who have looked at these systems and seen these types of R versus T curves, this can easily go to rather low resistances, right? Especially if the system is clean, you have basically ballistic transport. But, probably what's happening is, and this is data from 1960 on just, magnetic metals, as a function of temperature. Once you get to the Curie temperature, basically you can get a lot of scattering, presumably from magnetic fluctuations of that order. And so we think these are probably, this is kind of sometimes called critical resistance, and there's a million traces one can find. So like
Andrea, I have some questions on this because this is so fascinating, okay? I'm talking about data. I did not know about this old paper that you are showing here. I looked for physics like this. All I know is that in iron, cobalt, nickel, nothing happens to transport at Curie temperature. I mean, it's, you have to take many derivatives to see anything. Is that because it's at such high temperature that phonons dominate everything? So that whatever critical scattering you have is very tiny. You have to do a lot of subtraction. Whereas here, it's happening at very low temperature. So the critical scattering by magnons shows up right away. Is that the main difference?
I guess so. I mean, so I haven't dug through all of the old literature, and I don't have any sort of unified theory, but there's actually quite a lot of compounds that show this type of thing.
Oh, really?
And I'm happy to send you a few references.
Yeah, could you please? Because I looked for it. I asked everybody. Nobody knew anything. And
so I should credit Joe Czekowski and Eric Henriksen, both sort of separately pointed this out to me in different types of, and this is the one in this paper is good because this is exactly what it sounds like. Electrical resistivity of heavy rare earth metals. They just measured a bunch of them and a lot of them look like this. So
I think what happened, people who used to do these things are all like dead.
Totally, absolutely, yeah. This is just a lost fact that,
Because this is fascinating. Remember when you and I talked, I said magnon scattering usually doesn't contribute much, but I'm thinking at 900 degrees, maybe at 2 degrees.
Yeah, I think right? A lot of the ones that I've seen, I don't quote me on this, but a lot of the things that I've seen like this are all, in like the sub 200 Kelvin, sometimes lower range.
Please do send me these references. But
I'll send you that reference. Yeah,
your data are fascinating. It's just to the right, and something definitely is happening.
Yeah, and so let me show you sort of the last part of the talk, and then maybe that'll be a good, you know, entree to discuss this in detail, because sort of this was something that, you know, this was one fact that was bothering me for a long time. There's another fact that was bothering me for a long time that turns out we think is related.
Sorry,
So,
can I ask you a question about
sure.
this? So it's Victor Gilitsky. So there were these papers by Mason and Kapitulnik on molybdenum germanium, where they saw a huge drop of resistance, but to a constant, and then it remained metallic. I don't know if you're familiar. Actually, I will just put it in chat, this paper. And also in tantalum, they saw basically what you're seeing. And this, people were trying to explain it in terms of the so-called Bose metals. There was this huge, actually Matthew Fisher back in 2005 or so, he was very excited about stuff. I don't know if you are familiar with these types of experiments where people saw something that looked like superconductivity, but was kind of failed superconductivity. So,
I mean, I'm familiar with them. I am reluctant to say, I don't think this is failed. You know, I can tell you what I think, and then I can try to substantiate a little bit in the last, you know, 10 minutes or so. But I don't think these are failed superconductors. I think they're just not superconductors at all. That I think this is magnon scattering, and I think that whether or not then it becomes a superconductor just has nothing to do with this really directly, right? It's an interesting sort of experimental fact is that we know that if you have just if you make samples basically the same way, and there's nothing interesting going on, then it is not hard to get zero resistance at zero temperature. It's called, you know, ballistic transport, and it happens all the time. It's also true that it is basically impossible to measure a Meissner effect in 2 dimensions. So, you know, if your signature of superconductivity is just R as 0, but you have a very easy confounding experimental signature that's very common in these systems, which is R as 0, then, you know, you need to be more careful about how you claim a superconductor.
So, I mean, I was actually referring to a more exotic scenario, which again, Matthew and others were discussing maybe like 15 years ago, where there is actually formation of bosons, but they don't.
Yeah, I'm familiar. I think that might be relevant in some places in the phase diagram. It's
okay.
How to put it? It's not the point I'm trying to make. It might turn out to be relevant somewhere. In particular near nu equals -2, and maybe there's some analogies, but I think that thinking about the experimental data as a whole, there's actually a more generic thing that needs to be taken into account before one starts to, you know, try to, there's some null hypotheses to exclude, I think, for a lot of just basic interpretation of experimental data. And that's sort of what we were trying to do here.
But Andrea, I have a question or perhaps a comment. I think you'll come to it, but I just want to make sure. Are you saying that all the claimed superconductivity in this system could be this physics? Or are you saying that, no, there are situations where this happens and there are situations where there is pure superconductivity? Because you have Fraunhofer in some of your other samples.
Correct.
Right?
So I think that twisted bilayer graphene near nu equals -2 and +2, and, you know, in one sample measured once in Barcelona near nu equals 0 is a superconductor.
Okay, good.
And I think nothing else is a superconductor.
Right, but that physics possibly has nothing to do with this physics. Does not have to have something to do with this physics.
It doesn't have to. It doesn't have to. As a matter of fact, I think it does, but let me get to that at the very end.
All right, good, thanks.
Okay, yeah. Okay, so, right. So fact one is that a lot of these systems have these kind of resistivity drops, right? But then you don't see what Shankar was referring to was, you know, in the low temperature state, do you see a clear critical current? Do you see evidence of like Fraunhofer-like oscillations? Could you make a Josephson junction out of it if you put a local gate? You know, those are things that sort of confirm that you have superconductivity. A lot of these systems simply fail to show that, even though sometimes they have this type of dip, and sometimes that dip goes to 0. There's another fact which I've always found weird in this system since the very first measurements, which is, so here I'm showing you a sort of, again, a typical, this is a more updated sample, so it's very clean, a typical twisted bilayer sample, meaning resistive state at nu equals -2, +2, +3, peak at charge neutrality, superconductivity. Here's the type of Fraunhofer-y sort of pattern in the critical current that, that Shankar was talking about, right? No orbital Chern insulator of the type I've told you about, no quantum anomalous Hall, no obvious ferromagnetism, you know, in the sense of like an icing spontaneously broken time reversal symmetry is obvious to an experimentalist type of ferromagnet. And interestingly, no obvious symmetry breaking at nu equals plus and minus 1, right? So in particular, if you look at, this is from nu equals 0 to nu equals minus 2, and you look at the Landau fans, they're basically 4 or at very low fields 8-fold degenerate from nu equals 0 all the way to nu equals minus 2. There's not an obvious new state that appears there, okay? If you turn on a magnetic field, then you can actually make it, you know, you can find a Chern number 3 state there, but it doesn't happen until, you know, several Tesla. At 0 magnetic field, there doesn't seem to be any symmetry breaking at nu equals minus 1. Or at least not isospin symmetry breaking of the type that you associate with nu equals minus 2 or minus 3, where you actually have independent Landau fans that extrapolate to this new filling for each of those fillings. Okay, but sorry, you know, let me show you the experimental mystery here before I tell you a little bit more. But the puzzle here is that even in all of these samples, if you heat the sample up enough, you will find that there is there are now sort of oscillations that appear to be commensurate with the superlattice at, you know, nu equals minus 1, minus 2, minus 3, about, not exactly nu equals minus 1, not exactly, but there's a new resistivity feature that appears right around nu equals minus 1, when, as I showed you, at low temperatures, there's no sign of anything in the transport at nu equals minus 1. Okay, it turns out that, you know, you can access this sort of broken symmetry state also by in-plane magnetic field. So what I'm showing you here is a function, same sample, measured as a function of in-plane magnetic field. And you can see that there was not much going on at 0 in-plane magnetic field, but as you turn on a magnetic field, you see a new resistivity peak appear and kind of move towards nu equals minus 1. This is also evident in the Hall density. So this is the Hall density as measured. And actually, we decided to analyze this data by looking at the Hall density, subtracting off what you would get for monolayer graphene, meaning subtracting off this line. And you can see that what happens is that the Hall density is basically flat all the way to nu equals minus 2 when you switch how many flavors you're filling. And there's a sort of nice treatment of this from the Weitzman group of what they think is going on here. And I agree with that, where you're essentially, you can take a kind of quantum Hall ferromagnetic Stoner model and just adapt it to the fact that the bands have a Dirac-like linear density of states, and you can sort of understand why you would have these steps in the Hall density. That's consistent also with compressibility data. And in an in-plane field, you develop a new step near nu equals minus 1, as if you are in fact now favoring not just an unpolarized phase and then let's say a 2-flavor phase, but a 3-flavor phase in the middle. Okay, and so this sort of looks like this, right? Here you have no flavor. This is as a function of perpendicular field again. Here are the quantum oscillations, no flavor symmetry breaking, but then as a function of large enough magnetic fields, let's say up to, you know, above 5 or 6 Tesla, you get a new flavor symmetry broken phase. Okay, so then you have this high temperature puzzle, right? Of, you know, is this actually a situation where you have temperature induced flavor symmetry breaking? It's kind of strange, right? So, you know, but the analogy is kind of relatively sharp because it seems like anything you do to the system, you can put on an out of plane field, an in plane field, or increase the temperature, and you get something that looks like a symmetry broken phase at nu equals minus 1 that's not there at 0 temperature, 0 magnetic field. Okay, here's what the data looks like as a function of temperature. You can basically trace the resistivity maxima and kind of try to construct a phase diagram, and you find that, okay, down here is superconductivity. This is within the 2-flavor phase. Here is a new 3-flavor phase, we would say, that emerges in between, and then here's our 4-flavor symmetry unbroken Fermi liquid that is close to charge neutrality. And this is also evident. You can see these extra kinks in the Hall, in the subtracted Hall density that appear that are not just thermal broadening of the 0 temperature state. It looks like there's actually some extra kinks that are appearing. Okay, so what to make of this, right? So we came up, Eresberg and I, with a sort of basic picture for what might be going on. Okay, so the basic picture is that, what's known from theory and of course also from experiment is that these systems are inherently, there are a lot of states in close competition with each other, right? What's the actual ground state depends in extreme detail on the twist angle, on alignment to substrates, on more or less anything you do, magnetic fields, pressure, and so on, right? Everything is very finely tuned. It seems as if generically nu equals -1 is not an ordered state at 0 magnetic field and 0 temperature. But we know from the magnetic field dependence that there's apparently a state that is polarized that is not very far off in energy because, a few Tesla magnetic field in the plane will put you into that polarized phase. And that is just not a huge energy scale, right? That's of order 5 Kelvin worth of Zeeman energy. Now, in a finite temperature, of course, you don't just care about the ground state energy. You actually, you'll get a first order phase transition if the free energy of 2 phases is the same. Okay, and so you can think about this isospin unpolarized phase. It's a Fermi liquid, and it'll have an entropy proportional to temperature as a Fermi liquid does. On the other hand, in the isospin ferromagnet, if you fully disorder it, then that's a lot of entropy that it can now have, right? It can have some entropy that's log of the number of modes roughly, or the number of degrees of freedom that those isospins actually have, which is a theorist-dependent concept, but it's in a log, so it doesn't really matter. But it's an entropy of order 1. This n might be 2, 4, 8, something like that. So you have some scenario where you could get, a kind of order by disorder, where as you increase the temperature, this above, let's say, the pseudospin stiffness of whatever that isospin ferromagnet is, it mostly disorders. Maybe there's some residual magnetization. But that big change in entropy relative to the Fermi liquid is enough to lower its free energy and make it now the favored state at some finite temperature, and then you get a first order finite temperature phase transition. So a key thing here is that you need a pretty low pseudospin stiffness, right? Or spin stiffness. It's not clear actually what the most relevant modes are. This seems to be okay. So here's that, the key thing here is if you're looking, let's say, at dispersions of neutral modes, the pseudospin stiffness is basically the bandwidth of some of these modes. So you can see this is a paper from Shankar and Fengcheng, and the 5 MeV is the total bandwidth. There are other calculations that suggest this is even smaller, right, for different types of modes. It depends rather strongly on which particular ground state you choose. Theorists seem to be able to calculate this for a given gap state in one approximation or another, but generically they all find relatively low pseudospin stiffness, somewhere between 1 MeV and 5 MeV, sometimes smaller. So this seems promising, right? It seems possible that in fact this high temperature phase is in fact kind of a mostly disordered isospin ferromagnet, right? It turns out that this is of course like a very well-known effect, right? Although not that well-known these days because dilution refrigerators became good and the Pomeranchuk refrigerator has kind of fallen out of normal use. But actually this is the mechanism underlying the Pomeranchuk effect in helium-3. And what happens there, and this is from Pomeranchuk's 1950 paper where he predicted this, he's simply plotting the entropy of a Fermi liquid and the entropy of the solid phase in helium-3. And the basic intuition here is that in the solid phase, the nuclear spins have very little overlap with each other. And as a result, the exchange interactions are very weak. And as a result, the spin stiffness is very small, which means there's a very low temperature where those spins could disorder. That entropically favors the solid. And so for a kind of fine-tuned range of parameter space where these ground state energies are very close, you can get a finite temperature phase transition from a liquid into a solid. And then of course at higher temperatures, the solid melts again, right? So we think that's basically analogous to the physics that's going on here, where the kind of interesting fact is that in these isospin ferromagnets, the spin stiffness, pseudospin stiffness, essentially the bandwidth of these neutral excitations is very small. And as a result,
so Andrea, quick question.
You can disorder it and that favors a defined temperature. Yes, Shankar.
Andrea, a quick question. So, this is something I think I asked you, but maybe I didn't. So there should be really two obvious temperatures in an experiment. One is this lower temperature melting or freezing, and the other is the higher temperature melting or freezing, because it enters, then it goes out again. Is there, I mean, can you point to that in the data that you have two characteristic temperature scales? There's so much going on that I could not figure that out.
Yeah, well, I would say that, you know, okay, if I'm going to stretch the analogy to helium-3.
No, stretch it, yeah.
Yeah, I would say that the problem with observing this temperature scale here is that your nuclei in helium-3 would actually break apart at some point, right? That in other words, like the energy scales where the energy scales of the Coulomb interactions are on the order of 100 or 200 Kelvin, right? In a sense, that's where you'd expect this kind of high temperature quasi-ordered phase to first start to emerge. But 100 or 200 Kelvin is also the energy scale of the isolation of the gaps to the next bands.
Oh,
and so I think look, if you keep going to higher temperature, and I think this is there, you know, at 100 or 200 Kelvin, you certainly stop seeing these wiggles at some point, right? But they can onset at 100 Kelvin and then they'll be gone. Now, whether that's because they're really gone in a flat band only picture, or you're now just exciting we know at that point you're exciting a lot of carriers from the dispersive high energy bands. I don't know, but yes, you do. If you know, this was in our paper on linear T or linear-ish T, right? At high enough temperatures, these wiggles are gone. So they're there sort of from 10 Kelvin to 100 Kelvin, and then they disappear, and that's a bit sample dependent. But yes, yeah, I mean, they do go away, but there's other effects that are onsetting there. So I don't want to say it too strongly, but yeah, I think that's basically correct. You know, in the picture here, this would be something like order the Coulomb scale, which is like 100 Kelvin.
Okay, I get it. Yeah.
Okay, so something that we realized in thinking about this is that you know, we now, let's say we take this picture seriously and we say, look, this is a first order phase transition, and there's two ways to actuate it, right? One is to change the temperature, which then favors entropically this, you know, this sort of disordered ferromagnetic phase at zero magnetic field. And the other would be to actually change the ground state energies by doing this at low temperatures, but change the in-plane field. Well, that allows you to measure the ground state energy difference, which is delta E, is just the Zeeman energy at which you get this transition for a given filling factor, and measure the entropy difference by measuring the temperature at which you get this at zero magnetic field. And if you put those together, you get a very simple relationship where the entropy change across that phase transition is just the ratio of that Zeeman energy where the phase transition happens at zero temperature to the temperature where that phase transition happens at zero Zeeman energy. And so you can plot these, and basically what you find, and the key thing here is that, you know, I'm plotting these just on the same scale in units of temperature as a function of filling factor, and you find that they basically track and that they're basically the same size, right? So what that means is that delta S is just about 1. And just to be clear, this is measured in units of entropy per superlattice unit cell, right? So you're getting an entropy of order 1 per superlattice unit cell as the difference in entropy between this Fermi liquid, which has no entropy of isospins, and the isospin ferromagnet, which basically means that this is a very strongly fluctuating ferromagnetic phase. There may be some residual magnetization, but not a lot. This is, you know, again, it's rather large. And recently, you know, picking up these ideas, Shahal Ilani's group basically did a measurement of d mu dt and extracted the SDN in a very similar situation. And they indeed also found that, you know, that the change in entropy is of order 1 from sort of a thermodynamic measurement. So this picture seems to be roughly correct, or at least consistent across those two experiments. Okay, so let me sort of wrap up and ask, you know, maybe pose some questions and speculations at this point about what this all means. So I think one interesting thing is, okay, if these spin waves are really there and they really are driving this transition into this strongly fluctuating ferromagnet, then the strong resistivity features that we saw and generally see in these systems would seem important to consider magnons and their role in scattering in those, right? An interesting thing is that we think this is essentially ubiquitous physics, right? I don't think this is special for nu equals anything in particular. I think this happens all the time, that, you know, at high temperatures, just as in high magnetic fields, everything is basically a ferromagnet. And so that would sort of explain the ubiquity. It also kind of makes sense that these are not, they're not really linear. I mean, we sort of, even when we were analyzing this data, you know, everything is linear for a sufficiently small range of temperatures. There's a lot going on. The basic point is that the resistivity is large, the low temperature behavior is highly non-universal, and those two features seem to me consistent with low stiffness magnons everywhere. The details are going to determine exactly what happens at low temperatures, but you generally expect, for example, large scattering to onset at quite low temperatures, perhaps lower than what the phonon Bloch-Gruneisen temperature would be. And then you'd expect the effect to be relatively large. And, you know, as we discussed at length with Shankar, when you try to fit data to phonons, you do have to fudge the deformation potential by a kind of a large margin. Nobody really knows what that is, but at the same time, there's certainly plenty of room in the theoretical understanding for more scattering mechanisms in these systems. There's a puzzle here. I'll say this to this audience because I think you guys will be acutely aware of maybe the importance of this, which is that, you know, in this paper, you know, we pointed out that actually these large resistivity effects, this big enhancement of this kind of linear T resistivity is actually in some ways equally important well away from magic angle as it is at magic angle. So one of the questions that I have is whether, in fact, isospin fluctuations play a role even when you're rather far from the flat band. In other words, when there's no obvious evidence for correlated physics or commensurability physics at any temperature, does this still matter? Because after all, the linear T resistivity in particular at 1.2 degrees was still a very strong effect, even though there was absolutely no sign of any of this ferromagnetic physics. So that's something that I think we can address experimentally by combining these types of entropy measurements with transport in, you know, samples well away from magic angle, and that's something that I think we're going to try to do. I think that, to me, it's relatively clear that these kind of quote-unquote fake superconductors are probably coming from magnon scattering. This applies to kind of rhombohedral graphene on HBN, twisted double bilayer graphene, twisted mono bilayer graphene, probably other systems, tungsten selenide heterostructures, and so on. I think that's probably likely, and that should be sort of the null hypothesis to reject. And that, in fact, this kind of like ferromagnetic physics is the thing that's generic, and superconductivity might be quite a bit more special to twisted bilayer graphene. Speaking of which, I think that, you know, I think maybe this is something that should be thought of. I mean, one of the things that I think would be beautiful if true is that our measurements and this general picture, I think, do imply a very low pseudospin stiffness, maybe of order 5 Kelvin. And that's kind of a prerequisite for some of the more exotic pictures of superconductivity. For example, this idea that superconductivity is really kind of an exciton condensate of skyrmions for the right type of ground state. These types of mechanisms all rely on having a very low pseudospin stiffness. Doesn't mean they're true, but they probably wouldn't be true if this weren't true. So so that's good. I think the last thing is that, you know, in terms of analyzing this data, one of the things that's become abundantly clear is that you don't need to see a correlated insulator in order to know that you have, you know, if you have isospin symmetry breaking, it does not imply that the isospin symmetry breaking is most strongly oppressed at integer filling. It can be happening away from integer filling and not happening at integer filling because of detailed energetics of these different phases. So it's possible that the Fermi surface is indeed reconstructed away from integer filling, but that at integer filling, it's back to being an unpolarized Fermi liquid. This is actually a kind of a trivial point, but it was hard for me to understand coming from quantum Hall ferromagnetism, where essentially the Landau levels are relatively featureless. And so if you don't see anything happening at integer filling, it's unlikely that things are happening away from integer filling that are more interesting in terms of isospin symmetry breaking. But here, because the density of states has sort of a funny shape in the single particle band structure, I think that it's kind of obvious why that happens. And I think we understand now experimentally how to look for it in these kind of subtle features of the Hall density and so on. That's sort of become a little bit clearer to us. So anyway, let me conclude with that, and thank you all for your attention. I'm sorry I ran a little bit over.
Thank you. Now it's open to all for questions.
Oh, hey, Andrea.
Hey, Jay.
Yeah, can you elaborate the Fraunhofer? I mean, you made the point about the Fraunhofer, and I guess for those who are following very closely the field, this is obvious. But so, what's the Fraunhofer distinction between a superconducting phase? So
yeah, so I mean, this is not a great example because, of course, you know. All right, so if you look at the original data from MIT, right, they had a really important thing, which was that if they just looked at critical current as a function of magnetic field, they saw very clear oscillation, okay? And they look like you have a squid or a Josephson junction, right? And presumably this comes from inhomogeneity in the sample, and you have some kind of junction-limited superconductivity. It's random, it's messy, sometimes it looks nice, sometimes it doesn't, but these types of, you can sort of resolve periods here, right? In this, if you look closely, and sometimes that's obvious, right? It really just looks like a squid, or, you know, and you can find this in lots of the papers. I think that's a pretty good sign of superconductivity. Okay, because you know, you have a non-uniform system, and then you have weak links kind of scattered in it, and some of which dominate the resistance. And if you just had a ballistic metal, it's less likely that you would see that. Of course, you can still see, like, you know, phase coherent effects, but in terms of it modulating what looks like a critical current, that's less likely. Okay, so this is sort of as close to a smoking gun for superconductivity as basically those types of Josephson junction looking things. Recently, I saw there's some data where you do this intentionally, and yeah, it looks like Josephson junction, so as it should, right? I mean, it's a superconductor. But in many of these other systems, it's not observed. There are a number of other weird features that are observed that, you know, I think the best reference for this is this paper from Matt Yankowitz at UW recently, where they basically look at twisted double bilayer graphene and sort of show that it really can look like a superconductor, but these are not superconductors. These are just exactly, I think, that I just told you. So I think now we understand why. What they were pointing out in great detail is how they're not superconductors, even though they look like it. There's a number of other features. I'd refer you there because that's the most thorough treatment of
sure. Yeah, thank you.
that problem. Yeah.
Sure. Great. Thanks.
So Andrea, let's get back to the issue of the high temperature resistivity, which is, as you know, right from the beginning, I thought magnons may be playing a role. But one problem I see, and Fengcheng and I talked about doing a calculation also some time ago. Problem would be that first, the calculation is quite tricky because these magnons are not really, they are not really like a background bosonic bath. You know, phonons are a background bosonic bath. So scattering is very easy to calculate. Magnons are coming from the electrons themselves, right? It's the electrons themselves ordered in some manner, and it's the collected modes of electrons. So one has to be very, very careful what one is doing. But let's say that as theorists, we make some approximations that we believe in. But we'll run into the same problem that you alluded to for electron-phonon coupling, but even more so here, the coupling constant. Because as you said, and as we know, that you know, it depends on all the details. So perhaps the best one can do is to show some kind of consistency, meaning that the same coupling explains the low temperature drop in resistivity and the high temperature linearity in resistivity somehow, you know.
Yeah, that would seem like a reasonable thing to do. I think the let me try to find the, oh, it was back here. Yeah. You know, there's some things that are puzzling. So yeah, let me remind you, this is in this monolayer bilayer graphene. And over here is where we think it's basically just kind of regular old band metal physics, nothing too narrow, nothing too interesting. And you can see, for example, there's no jump in the blue or the red curves, but actually the slopes of those curves are not any smaller. So that's a puzzle, right? You know, in other words, I think that these big jumps are probably pretty robust signatures of, you know, disordering of magnetic states of one kind or another. Whether, for example, the d rho dt is also related to that, I think experimentally there are a few things that just don't make that are puzzles. One is that, you know, well, the simplest is that when the bandwidth is not so narrow, you still see a big d rho dt, and that's true also in twisted bilayer graphene. When you tune away from magic angle, it's still quite big. It's not as big, but it's still very big compared to what you naively expect from phonons with a naive deformation potential.
Is that data in your original paper?
It is, right? At one, you know, if you remember, right, we took your curve and we had to multiply the deformation potential by 3 everywhere, including away from magic angle, which was why we were so convinced that, like, it can't be that important. Now, it could be that magnons are important even away, you know, away from magic angle is not that far. We're talking about, you know, 1.2 degrees. It's not crazy that could still be important, but that's something that I think there are similar scenarios. For example, you know, understanding this when there's not obvious symmetry breaking at low temperature, but perhaps that's just an energetics thing. Maybe it never quite orders, but it's, I don't know. You know, that's sort of my question.
Well, I think that you have made a compelling case, at least for me, showing this old paper also. Because I thought about it, I said, it cannot be magnons. Because in iron, I'm telling you, if you go to iron, people have talked about critical scattering and all these things. It's like you have to take like 2 derivatives to see anything. But these data clearly show that there are other materials, whatever this is, dy. I don't even know how to pronounce it. The effect is huge. I mean, look at this. It's going from like 1 to 100 almost. It's a factor of 100. So it looks
this is sort of the most extreme example I found when I was putting this talk together. But yeah, I think this is a literature that should be looked at. And
you're sending me some of these papers.
I'm going to send you. I'll send you a couple that.
So you'd say that doing a magnon calculation, doing a reasonably honest theoretical magnon scattering calculation for your system would be quite useful.
I think that's super useful. Yeah, I don't know how easily it can be done given this problem of, you know, they're not like you know,
it's easy. I don't want to do it.
If the bandwidth is 5 Kelvin, then what does like the soup of interacting bosons look like? I don't know. Yeah, but that's, you know, that's
my concern is the issue of vortex correction. You know? Anyway, but that's a theoretical question. It sounds
that's a theoretical question. Yeah, I think it would be useful to understand what the magnitude of those effects are.
Right.
And, you know, ultimately, I think that it would be very interesting to understand. I mean, you know, again, I don't know well enough exactly the approximations in which one calculation is done or another. This is done for nu equals 3. This is done for nu equals 0. They get different answers. That's probably reasonable, but, you know, presumably just thinking about what is the effective pseudospin stiffness as a function of density for different ground states would tell you that would also be interesting information, right? Because if you recall, you know, the density dependence is really quite, you know, quite striking in these systems.
So I have a second question, which is unrelated, but actually is not unrelated. So this presence of ferromagnetism, which I think is very compelling now, based on this Pomeranchuk physics. What does it tell us about superconductivity? After all, you can have superconductivity, BCS superconductivity mediated by magnons. I mean, you know, this is high TC. This is what Chubukov has been talking about. He puts it somewhat differently, and I find it very believable. So,
seems reasonable to me. I don't know. I mean, I think, you know,
But I thought that where you see superconductor, the feeling where you see superconductor, you're not seeing this Pomeranchuk effect, right?
So let's see. So this is as a function of temperature, right? The thing is that where you see superconductivity is between nu equals -2 and -3.
Mm-hmm.
I would say that there you think you're in some kind of, you know, twofold phase, right? So like this is, I would call it like, I think we called it IF2. So isospin ferromagnet with two flavors filled, right? And this one is IF3. Now, what is the entropic difference between these two that's making this transition move a bit to the left? I don't know. That's you know, here it's easy to understand on side because this is basically unpolarized Fermi liquid, right? So here it's Pomeranchuk in the sort of Pomeranchuk sense. You have Fermi liquid and then you have some kind of magnetic, you know, paramagnetic or fluctuating ferromagnetic phase. Here it's ferromagnets all around. So, you know, this would be IF1 where you have one flavor occupied. So, I mean, this is all details is going to determine exactly what happens. Clearly something is happening. So yeah, it's a good question.
So
we're going to study this in some detail.
But even that aspect then is worth looking into. What about
a
calculation similar to, you know, what Finching and I did, but more elaborate? What is the physics of magnon-mediated superconductivity here?
Yeah, so what I would love, just as a simple thing that I would love to see is, you know, what we're now measuring in a very similar sample, entropy as a function of temperature. And with, you know, that has all of these features, you know, it has superconductivity, it has all of these different things. So a question that I have is for a given ground state, what is the entropy as a function of temperature? Once you have those neutral modes, I guess you can at least approximate it at low temperatures. Sure. Maybe there's something more elaborate you can do. Mm-hmm. That is something we can directly measure. We can directly compare to transport. And that's sort of where we're going with this in terms of an experiment that's immediately accessible that we can try to do.
Very good. Very good. Yeah, by the way, you did answer my question. Those imaging data, that's an amazing experiment with that squid. I mean, I think you told me that was going on when I was in Santa Barbara, but you are not sure what the outcome would be. But it looks. Yeah,
like... I would have told you that 3 years ago too. This is really hard. It was a really hard one. I'm very glad it finally finished.
Yeah, it could not be done. But you told me it's going on, and it's looking very optimistic. But it looks like it was successful.
It worked, and it was definitely on the edge of what we were able to do. So
I would say that, you know, I accept that as fairly direct evidence for ferromagnetism here. Magnetic moment is small, but I think you clinched it. Yeah, thanks.
Thanks.
Oh, hi. So now is time to close the seminar section, and thank you for your wonderful talk. I will stop recording now.
But we are meeting in the same Zoom, right?